Ready to dive into something different today.
Always up for a challenge.
This time, we are looking at how things are made.
You mean like factories and production lines?
Yeah, exactly. There's this new research paper arguing that all that meticulous planning maybe isn't the best way to be efficient.
Really? You're saying a little chaos could actually be a good thing?
That's the idea they're proposing. They call it self-organizing production systems. SSOP for short.
SSOP. Huh. So instead of trying to predict every little thing that could go wrong, you just kind of roll with the punches.
Basically. I mean, think about it. Traditional production planning is all about sticking to the schedule.
Right, predicting the future, what to make, when to make it, which machines to use.
Exactly. Sounds great in theory, but in reality.
Oh, it never goes according to plan.
Never. There's always something a machine breaks down. A delivery is late, somebody calls in sick.
And that's just the tip of the iceberg. This paper actually lists 12 reasons why production deviates from the plan.
12. They did their homework.
They did. And get this, they even use math to show how even small disruptions can snowball into huge delays.
Okay, I'm sensing a but coming.
But it's not just about things going wrong. It's about the uncertainty that messes everything up.
So this is where SSOP comes in to save the day.
Exactly. Because it acknowledges that uncertainty is a fact of life, and it tries to work with it instead of against it.
Okay, so how does it do that?
Well, first we have to understand that not all uncertainty is created equal.
You mean there are different types of uncertainty?
There are. The paper talks about two main types, aleatory and epistemic.
Aleatory and epistemic.
Sounds complicated.
It's not as bad as it sounds. Think of aleatory uncertainty like flipping a coin.
Okay.
You know, there are only two possible outcomes, but you can't predict which one it'll be.
So it's like random chance?
Exactly. Like material defects, you never know which items will have flaws.
Makes sense. So what about that other one, epistemic uncertainty? What's that all about?
That one comes from a lack of knowledge, like missing information.
Can you give me an example? Imagine trying to assemble a piece of furniture, but you're missing some screws.
Been there.
Right. You have a general idea of what to do, but you can't finish it without those missing pieces.
So epistemic uncertainty in a factory setting would be like, what?
It could be outdated information about a supplier's stock or inaccurate data about a machine's performance.
Basically anything that throws a wrench in your plans because you didn't have all the facts.
Exactly. And the thing is, traditional production planning just isn't equipped to deal with either type of uncertainty very well.
So it's like trying to navigate a maze blindfolded.
Pretty much.
So how do we take the blindfold off?
That's where SSOP gets really interesting, because it says instead of fighting the chaos, we should embrace it.
Embrace the chaos. That sounds kind of scary.
It might sound counterintuitive, but think of it this way. Chaos doesn't have to be a bad thing.
Okay, I'm listening.
It's about designing a system that can adapt and thrive because of its complexity, not in spite of it.
So we're not trying to eliminate uncertainty, we're trying to work with it.
Exactly. And to understand how we can actually do that, let's talk about this other cool idea from the paper. Deterministic chaos.
Deterministic chaos. Now that just sounds like a contradiction in
It
terms.
just does, doesn't it? But it makes sense when you think about it this way, even though things are technically predictable.
Like a ball rolling down a hill.
Exactly. We know the laws of physics that govern that, but even the tiniest change in the initial conditions, like where you place the ball or how hard you push it.
Can have a big impact on where it ends up.
Exactly. And in a complex system like a factory, those tiny changes can ripple outwards in ways that traditional planning just can't handle.
So it's like the butterfly effect, but for factories?
Exactly.
Right.
A small delay in one part of the system can snowball into a major disruption somewhere else.
And SSOP is supposed to prevent that from happening?
Not prevent it. Exactly.
Yeah.
More like adapt to it.
So are you saying we just need to accept that chaos is inevitable and there's nothing we can do about it?
Not quite. It's more about recognizing that trying to predict and control for every single variable is kind of a fool's errand.
Like trying to herd cats.
Exactly. There's just too much going on, too many moving parts.
Okay, so what's the alternative?
Well, this is where the research gets really interesting, because it looks to nature for inspiration.
Nature. What do you?
I mean, it literally draws parallels between self-organizing production systems and the way that ants, swarms, even slime molds solve problems.
Slime molds. Hold on. How can something that sounds like it belongs in a horror movie teach us about efficiency?
It's pretty wild, actually. Slime molds are these single-celled organisms, but they can form these incredibly complex networks.
Okay.
And they can do some pretty amazing things like finding the shortest path through a maze or even optimizing transportation routes.
All without a brain. How is that even possible?
That's the thing, they don't need a central brain because they're relying on distributed intelligence.
Distributed intelligence. So, like, each part of the organism has its own little brain.
Kind of. They communicate through chemical signals, essentially leaving trails that other parts can follow.
So it's like each individual part is acting on local information, but collectively they're achieving something much greater.
Exactly. And that's the key to how SSOP works, too.
Right.
It's about creating a system where the individual parts, the machines, the materials, the workers, can all communicate and adapt locally.
So instead of having one central computer calling all the shots, you have all these different agents making decisions based on what's happening around them.
Precisely. And because they're constantly sharing information, the system as a whole can be much more responsive to change.
Okay, I'm starting to see how this could work. But what about those attractors we were talking about earlier? How do they fit into all of this?
Good question. Remember how ants lay down pheromone trails to guide the colony to the best food sources?
Yeah.
It's the same idea with attractors. They act as these guiding forces that pull the entire system towards the most efficient outcome.
So instead of pheromones, we're talking about information flows.
Exactly. Imagine a factory floor where machines can signal when they're nearing capacity, materials can call for replenishment when stocks are low, and workers can see real-time updates on their tablets.
So everyone and everything is always in the loop.
Exactly. And because of that, the system can adapt to disruptions much more smoothly.
So if one machine goes down, for example,
The other machines can adjust their output,
Yep.
materials can be rerouted, and workers can be reassigned without missing a beat.
it's like the system has its own built-in shock absorber.
Exactly. And that kind of flexibility is crucial in today's manufacturing world, where everything is constantly changing.
So it's like the whole system is constantly learning and adapting on the fly.
Exactly. And that's what makes it so much more resilient than traditional approaches. But speaking of adapting, there's another important aspect of this we should discuss.
Go on.
Well, we've talked a lot about the technical side of things, the algorithms, the agents, all that. But what about the human element?
Right. We got a question from a listener who's wondering about that too. With all this talk about self-organizing systems, they're worried that human workers will get left behind.
I get it. It's easy to imagine a future where robots take over and humans become obsolete.
So is that what this research is suggesting?
Not at all. In fact, the authors are very clear that SSOP is not about replacing human expertise. It's about enhancing it.
So it's more about giving people better tools and information to do their jobs.
Exactly. Think of it this way. Instead of having to constantly react to problems and put out fires, workers can focus on more strategic tasks.
So they become more like conductors than musicians,
Mhm.
guiding the overall performance, but not necessarily playing every single note.
That's a great analogy, and it highlights something really important about SSOP. It's not about eliminating human input, it's about making that input more valuable.
Okay, that makes sense. But how do we actually get from this theoretical model to a real-world factory that runs on SSOP?
Well, the paper actually provides a framework for doing just that.
Really? They get that specific?
Yeah, they do. They talk about different types of software agents, each with its own specific role to play in the system.
Like what?
So you've got contract agents, which handle things like customer orders and deadlines. Then you have resource agents, which represent the machines and their capabilities.
Mm-hmm.
And of course, storage agents, which keep track of all the materials and inventory levels.
And how does all this get coordinated? Who's in charge of making sure everything runs smoothly?
That's where the production agents come in. They're like the conductors of the orchestra, overseeing the entire production process and making sure everything stays on track.
So it's like a well-oiled machine with each part working together seamlessly.
Exactly. But the key difference is that this machine can adapt and adjust on its own without needing a human operator to constantly tweak the settings.
Okay, that all sounds very impressive in theory, but does it actually work in practice?
That's the million-dollar question.
Yeah.
And to answer it, the researchers ran a bunch of simulations comparing SSOP to traditional production methods.
What did they find?
The results were pretty convincing. In many cases, SSOP outperformed traditional methods by a significant margin.
Really? In what ways?
Well, for one, it was faster and more adaptable to change.
Which makes sense given what we've been talking about.
Right, and on top of that, it resulted in lower inventory costs.
So it's a win-win, more efficient and more cost-effective.
Exactly, and I think that's what makes this research so exciting. It's not just some pie-in-the-sky idea.
Mhm.
It has the potential to revolutionize the way we think about manufacturing.
So what's the takeaway here? What do we want our listeners to remember from this deep dive?
I think the biggest takeaway is that chaos isn't always a bad thing. In fact, when harnessed correctly, it can actually be a source of resilience and adaptability.
So instead of fearing the unknown, we should embrace it.
Exactly, because within that uncertainty lies the potential for innovation and growth. And who knows, maybe by embracing a little bit of chaos, we can create a more efficient, more sustainable, and ultimately more human-centered future for manufacturing.
That's something worth thinking about. And on that note, we'll wrap up this deep dive. Thanks for joining us.